In this video, we're going to be learning about the particulate nature of matter. Now, this sounds super confusing, but it's really simple. All this sentence is, in a normal person's language, is we're going to learn about solids, liquids, or gases. Okay, so how does this make sense then? Because matter is any substance on Earth, anything you can see, feel, or whatever. So, for example, the air around you, that's matter. The bed, that's matter. The floor, even that's matter. Anything existing is matter. And the particulate nature, this is pretty much just a phrase saying what this matter is made of, how the particles making up this specific matter is arranged, the nature of the particles of this object. So, for example, any object that you can think of, say this rock, if we were to look really close, we would know that just like every other object, it is made up of small particles. Now, depending on the particulate nature of those particles, so how they're arranged and stuff like that, that's going to determine whether it's a solid, liquid, or gas. So that's the purpose of today's video. So let me first ask you, let's see if you can identify whether these objects are solid, liquids, or gases, and then we'll go and look at why they are considered solid, liquid, or gases on a particulate level. Okay, it shouldn't be difficult. This should be pretty straightforward. So this right here, it's a rock, so we know it's solid, and we typically associate solid things with really hard, dense things that don't change shape, right? That's a solid. How about this bone? That's also a solid, right? Because it doesn't change shape. It's really dense. Now, what about this, the coffee? This is not a solid, right? We consider this a liquid. What do we consider as a liquid? A liquid is any substance that takes the shape of the container it is in. So, for example, this coffee becomes the shape of a coffee cup if it's in a coffee cup. Were we to put this coffee in a square-shaped cup, it will become the shape of the square-shaped cup. If we put the coffee, we spill it on the floor, it will become the shape of the floor, right? So a liquid takes the shape of its container. That's how we know it's a liquid. Because, for example, let's say we put this rock, a pebble or something, inside a cup. Will it become the shape of the cup? No, right? It stays the original shape that it was. So that's the main difference between a solid and a liquid, okay? What about, oh, that's a joke, that's a cat. So it appears like this is a liquid because the cat is taking the shape of the container it is in, but it's just a joke. How about humans? Are we solid, liquid, or gas? So that's actually a trick question. So initially you might think, oh, we're solid, we don't change shape, right? But actually we're a mix of all of them. We're solid, for example, our skull might be solid. But we are actually made of water 70%, so technically we're mainly liquid. But at the same time, we also have gases inside us. We fart, or whatever we do, we breathe in oxygen, exhale carbon dioxide, those are gases. So we're technically made up of all of them. Now, what about jelly? So this is a confusing one. People think, oh, it's kind of like a liquid, but it's also like a solid. The truth is, it's a mix. So they consider jelly's particulate nature of matter to be solid, liquid-like. But some people consider it just to be a solid, because if you were to put this jelly in another container, it wouldn't become the shape of that container. So jelly is a confusing topic, but this is kind of one of the exceptions. They're not 100% sure about it. But you can consider it to be a solid, because it doesn't take the shape of its container. Okay, so now we're going to get on to why solids are solids, why liquids are considered liquids, and why gases are considered gas. If you were to look at the particles that everything is made up, if you were to zoom in really close, this is what we would see in a solid. So a solid, the particles making up, is really close together, super closely bound together. And they're not moving, they don't change shape. So, for example, let's pretend this is a brick, and we put it in a cup. The particles won't move to take the shape of the cup. It will stay like that. It won't move. The bonds in between the particles are very strong. It won't change shape. Now, for a liquid, that's different. The particles are not so tightly bound together. The forces holding them together is not that strong. So when you put them in a container, they kind of flow around and take the shape of the container, right? For example, if you were to pour water into a cup, it will become the shape of the cup because the particles are not that strongly bound like a solid, so they rather move and take a different, more comfortable position, right? And a gas is even more free. The bonds are even weaker, so the gas literally moves up and down. Like liquids, the particles don't move up because they always have a small attraction to the ones below them. So you'll never have a glass of water where half the water's on the top bit and somewhere in the middle and some at the bottom. No, they're always falling towards the bottom, but the particles can flow around each other, as we know. Whereas a gas, they can actually completely leave each other because the bonds are so weak and they can move everywhere they want. Okay, so this is the basics of the particle matter of solids or liquids. Okay, let's gonna move this. Okay, to make sure you understand this, I have a table here with some properties, and I want you to guess. You can probably get all of them by yourself. So I want you to guess what you think it is, and most likely you'll be right. Okay, but I'll reveal the answers after you have a guess. So consider solid, liquid, or gas, and here we have some properties, and then I'll reveal here what the case is for a solid, for a liquid, and for a gas. Okay, so what would you say the distance between particles in a solid is like, and a liquid and a gas? Okay, so pretty simple. Close together, slightly further apart, because they can flow, and very far apart in a gas, right? That's pretty simple. Because if you understand all these properties, you pretty much nailed what solids, liquids, and gases are. So, and on a particle level. Okay, how about arrangement? And what I mean by arrangement is how they're structured, how they're organized, the particles. Okay, so in a solid, they're clearly organized, they're regular. You can see there's a pattern. Whereas in a liquid, there's no specific pattern. They can always change shape. They can always be in a different position. When I move the cup around, it will never be in the same shape that it used to be before. It always changes, consistently moving. Same with a gas. That's why it's considered random, the arrangement. Okay, what about shape? What I mean by shape is what shape the object takes due to the particles. So, does a solid... okay, have a guess by yourself. So a solid always has a fixed shape, and we know this because if you have a rock, no matter how hard you squeeze it with your hands, it won't just change shape. It stays the same shape, right? They don't change. They have a fixed shape because the bonds are so strong in between the individual particles. They won't move. How about a liquid? We know this is not fixed. They can move around because the bonds are slightly weaker. And actually, so depending on the shape, so the shape of a liquid depends on the shape of the container. Like I mentioned before, if the cup is so I'll show you here. This is a good way to show it. Say we have a small cup. Let's move this. Right now, the shape of the particles inside, because the cup is small, is like a rectangle. You can see, right? Because the shape of the cup is rectangular. What if we put these particles into a big cup? Will it stay like this, or will the shape change? So the shape will change, right? Because the particles are going to flow until they're at a very comfortable position due to gravity, right? So therefore, they won't be weird like this or something, or only take up the side like this. No, they will take up, as you know, the water will take up, or the liquid will take up the most comfortable position due to gravity. And so the particles will slide around each other until they're like this. So the shape can change depending on the container. So that's why I said it's not fixed, because it depends on the container. Whereas a solid doesn't matter. Let me show you. Like, for example, we have a solid, and we put it in a small cup, it will be this shape. If we put a solid in a big cup, it will still be that shape. It won't move. The solid, the rock will stay a rock, okay? How about the last one, a gas? So gas, if we have it in here, this is the shape, okay? What if we put the gas into a big cup? Will it stay like this? Will the shape change at all? Well, yes, the shape will change because these particles are continuously moving. Let me show you. So for example, say we have this one. This particle might decide to float there. Down might decide to float there. Down might decide to float there. So the shape is always changing because the particles move around freely since the bonds in between them are very weak. Okay? So it's not fixed. Also depends on the container. Next one, this is a tricky one. What about volume? Volume is pretty much a word describing the amount of space something takes up, right? So if you drink a large volume, like for example, you drink from a cup and the cup has a volume of 250 milliliters, that just means the amount of space the water is taking up. If the water is taking up more space, then you're probably drinking a more volume from a cup. So, for example, a solid, does its volume change? What is its volume? So based on this example, we know, say we put in a small cup, that's the volume. It's taking up that much space, right? What if we move it to a big cup? Its volume doesn't change. It still takes up exactly the same amount of space since the particles don't move around. So we know for a solid, so first I'll reveal this so you can, if you guess, ready. So for a solid, the shape is fixed. How about a liquid? So let's look for a liquid. So at first we put in a small cup. Right now it's taking up this much volume, right? What if we put it in a big cup? Okay, so like I said before, it's gonna move and change shape to take up the shape of the container, right? But it's still taking up the same amount of volume. Still the same amount of volume. So therefore, for solid and liquid, the volume will always remain the same. Okay, and the last one, gas. What do you suspect? So let's say we put it in, we have this one. Wait, let me do this first. Say we have these 5 particles, and we put it in a small cup. Right now it's taking up this much volume, right? Because the cup is limiting the particles from leaving. So we're pretending the cup is closed. So the particles can't flow out of the cup. If the cup is open, it would in theory be able to do that. But right now, since the cup is closed, it only takes up this much space. But say we put those same five particles in a bigger cup, now the volume is going to change because it's going to move. The particles are going to spread out because they move randomly, right? So the volume can change. It can take up more volume, or if it's in a bigger cup. So the volume of of a solid and a liquid will never change. Whereas for a gas, it can change because if the container is bigger, the particles will spread out and take up a bigger area, bigger volume. Okay, how about movement? Okay, this one is simple. Movement, solids move, vibrate. They don't move at all. They barely move because the bonds are too strong. Liquids move slightly because the bonds are weak, so they can flow past one another. Gases, they move freely wherever they want to. How about speed of movement? Okay, so the next two I'll do together, speed of movement and energy. So this is easy to understand if you think of a real life situation. Does a person with a lot of energy move fast or slow? So a person with a lot of energy moves the fastest, right? So particles, gas particles, have a lot of energy, and therefore they move really fast. They move wherever they want. They bounce off the wall, whatever they want to do. Whereas a solid has very low energy. The particles don't move at all. They're stuck to each other. They're not free. They don't have energy to go anywhere. They're being held together like a prison. Whereas a liquid has some energy, so the particles move around a little bit. Okay, so therefore, speed of movement of a solid is the slowest, and a liquid is a bit faster, and a gas is the fastest. And this is because the energy of a solid is the lowest, and the energy of a liquid is a bit higher, and gas the highest. Now, why is there energy in this order? This is because of the forces of attraction. Since in a solid, the particles are being held together so tightly by bonds, it has little energy. It's not able to move anywhere because they're being held so tight. So in a solid, the forces of attraction is really high. It's really strong. They're being held together really tight by these cuffs. Whereas in a liquid, they're not really being held that tight, so they're able to have some energy. Whereas in a gas, they're not being held together at all, essentially. So they have a lot of energy and can move anywhere they want. So these three are kind of considered together, okay? And you'll learn a lot about forces of attraction in another topic of chemistry. Right now, you just have to associate forces of attraction as like holding hands. In a solid, they hold hands really tightly, the particles, and here not really that much, and a gas is not at all. Okay, so if you understand these properties, then in terms of these particles of a solid, liquid, or gas, then you understand the three states of matter really, really well. But there's one more thing we need to do. One or two more things. So first, this will be quick. This is something you need to know, and you probably know a lot of this already. we're gonna use a water, because water can be a solid as it will become ice. It can be a liquid, and it can be a gas when it becomes vapor. What do you call it? So I'm just putting this glass here to represent this is solid and this is liquid and that's gas under the object. So here I hid some words to describe a process. What are we gonna call the process turning a solid into a liquid? Melting, right? When you melt ice, when you turn ice into water, you're melting it. So if the word is on top of this arrow, it's referring to the process to the right. So going from here to here. Where if it's at the bottom, it's going the opposite direction, from here to here. So to turn water into ice, we know that's freezing. You put water in the fridge and it will become ice. How about turning water into steam? You have to boil it, right? Or evaporate it using a kettle. How about the reverse? Turning this vapor back into water. That is called condensation. And we know that sometimes happens because you can see after you boil the water and it turns into gas, the gas will kind of go on your window and become liquid, right? Because the window is cold. And so the warm particles will be cooled down to become water again. And you can also see that when the outside of your house is really, really cold, but the inside is warm. So the particles inside your house will touch the window and cool down and become essentially water vapor. So you can see this, it's liquid droplets when it turns from gas into liquid. Okay, two more that you probably don't know is what's the process called when you turn a solid straight into a gas? So we're skipping the liquid phase. That is called sublimation. Sublimation, I mean. And the reverse, turning a gas into a solid, deposition. So these words you just have to remember. Okay, it's not common words that you use in everyday life because these are not common processes. They don't happen often. So sublimation and deposition. Okay, final thing. So consider this diagram. So here we have something called a heating curve. Heating curve. We're gonna only consider this heating curve is specifically for water because we could have used any other material. Right here we use water because it's simple. It has all three phases, all three states of matter. I could have used iron because iron can be a solid liquid and maybe if you burn it long enough it could become a gas. I could have used any material. So in this video we're considering liquid, but it's the same for other materials. Okay, so I mean we're considering water, but it's the same for other materials. So here's the graph. And this graph is important for you to know. It's called the heating curve and it's for water. So what does this graph mean? On the x-axis we have heat. So wait, before I go into that. So we're gonna consider water. So let's pretend we have a kettle, okay? And in the kettle we have a solid. We're putting ice into a kettle, okay? So ice at that moment is very cold. Its temperature is like -40, -20, whatever. And so at this point we call it what? We call it a solid, okay? Because ice is at this point a solid. But as you apply some heat, so say we're turning the kettle on, so as heat is increasing, its temperature is increasing. So the temperature is starting to increase a little bit. The particles are starting to move a little bit because as you apply heat, the kinetic energy, so as you apply heat energy, so that's the flame under the kettle, the kinetic energy of these particles, so these particles will start to vibrate and move more fast. And temperature is simply the speed of movement of particles. So as the particles move faster, the temperature of that object is increasing. Okay? So now we have the ice. We're applying heat. The heat energy is increasing the particles' kinetic energy. So the particles are moving slightly faster. And since the particles are moving slightly faster, the temperature is increasing. So you can see as we're applying heat, the solid's temperature is increasing, but it's still a solid, which means it hasn't turned into liquid yet. So we're going now from -40 degrees, and now we're approaching 0 degrees, and now we're at the point called the melting point. So any more heat beyond this point will cause the solid to melt. So we call that melting. So now the solid's temperature is not increasing anymore, but rather all the heat energy being applied, all this heat energy is causing the bonds in between the particles to break. So you can see this is the point at which these solid particles being held together very tightly are now slowly being turned into this kind of shape where the bonds are broken a little bit, so they're moving more freely. okay? Therefore, the temperature is not increasing. It's staying 0 until all the solid, all the ice is turned into water, okay? Into a liquid. So that's what we call this shape here. So now, once it's being turned into liquid, now the heat being, so once all of it has been turned into liquid, so right at this point, everything is in liquid. And at this point, if we apply, so now in the kettle we have water, so no more ice. And we know if we put our hand in now, the water will still be pretty cold because the ice was melted, but now the water is still pretty cold. And now if we continue to boil the kettle, the heat will make the water warmer and warmer, but no gas will be formed yet. The water will, have you noticed when you boil a kettle, the gas only gets formed near the end, right? So as we boil the water now, the liquid is getting warmer and warmer and warmer and warmer and warmer until it's at another point called the boiling point. Any more heat from this point will cause the liquid to turn into a gas, and that is called evaporation or boiling. Okay, so now it's a gas at that point. So, but before it turns into a gas, so now that it's at the evaporating point, any more heat is breaking these bonds even more, causing them to be even more far apart. And that's why you can see all the particles at the liquid stage. The particles can't move out of the kettle yet, but as soon as you break the bonds even more, the particles are moving more freely, right? Because gases can move freely, and so they move out of the kettle in the form of vapor. That's what you see after you boil the water. So that's it. That's basically, you just need to understand why the curve is shaped in this way, why it goes up and then standard, up and then standard. And if you look at it the reverse way, you will know. So if we go from gas and we remove heat, so we put it in the fridge, so we put the gas into the fridge, it will turn into water, and turn into a liquid. That's called condensation. And then again, if you continue to keep it in the freezer, it will turn into a solid. Okay, that's a reverse process. So you just need to understand why the curve is shaped in this specific way, and what applying heat means. And with regards to temperature, temperature is just the movement of particles. And as you apply heat, the particles are moving faster and faster and faster, so the temperature is increasing until this specific solid reaches a point where any more heat doesn't cause the particles to move faster, but rather the bonds to break. So now it's from this to this, and then again it increases temperature, particles moving faster, 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 until the boiling point at which any more heat causes the bonds to break and a gas to be formed. And now any more heat will cause the gas to get warmer and warmer and warmer, and there's no more phases after that. That's the last phase. And consider that this curve is specifically for water, specifically for ice and water and water vapor. I could have used, if I talked about something else like wood or something, this curve would have slightly different values because different materials have different melting points and boiling points. But this is the case for water, and this is a simple case we all know.